Point cloud registration is the backbone of SLAM, autonomous navigation, and 3D reconstruction, but it has a persistent generalization problem. Learned 3D feature extractors work beautifully within their training domain, but as soon as you switch sensors, change point density, or move from indoor RGB-D to outdoor LiDAR, performance collapses. The core issue is that 3D lacks a true foundation model. We have massive, heterogeneous datasets for 2D vision, but not for raw 3D geometry. So how do we get the robust, cross-domain matching capabilities of vision foundation models without fine-tuning a new network from scratch? The answer, as demonstrated in the recent C-GenReg paper, is to temporarily translate the 3D registration problem into the 2D image domain, solve it there using pretrained priors, and fuse the results back into 3D space using a principled probabilistic framework. The entire pipeline is completely training-free, zero-shot, and operates by routing data through off-the-shelf foundation models. Let's walk through the architecture. You start with a source and target point cloud. The first step is rendering depth maps from both. Instead of feeding these into another 3D network, C-GenReg passes them into a world foundation model, specifically Cosmos Transfer. This model is conditioned on the depth sequence to generate synthetic RGB images. The critical requirement here isn't photorealism, it's multi-view geometric consistency. The generated RGB frames must preserve the exact underlying structure across viewpoints. If the generative process introduces geometric drift, the matching stage fails. Cosmos Transfer handles this by leveraging world-scale priors that naturally propagate spatial coherence across adjacent frames in the depth sequence. Once you have these generated RGB views, you don't use a generic vision encoder. You use a task-specific vision foundation model like MAS-3R, which is explicitly trained for dense geometric correspondence. There's an important implementation detail here. MAS-3R uses a cross-attention decoder, meaning the feature representation it extracts for a source image changes depending on which target image it's paired with. To maximize viewpoint coverage, the pipeline samples a small set of K-frames from the generated sequence and evaluates all pairwise combinations. Because the generated frames are highly correlated, you only need a few representative views to saturate performance, which keeps computational overhead manageable. After extracting dense 2D features, the pipeline lifts them back into 3D space using the original depth maps and camera intrinsics. Since the generated image features are much denser than the voxel downsampled point cloud, the system performs a nearest neighbor query to assign each 3D point its corresponding 2D feature vector. This gives you your first set of geometry-aware descriptors. But we don't want to discard the raw 3D structure. In parallel, a geometric branch runs a pretrained 3D feature extractor, like GeoTransformer, directly on the input point clouds. Now you have two independent correspondence signals, one derived from the generated imagery and one from the raw geometric features. Traditional methods would naively concatenate these features before matching, which ignores their different inductive biases and treats them as equally reliable. C-GenReg does something more rigorous. It uses a probabilistic match-then-fuse strategy. Here is where the technical depth comes in. For each modality, the pipeline computes a source-target feature similarity matrix, then applies a row-wise softmax to convert it into a correspondence posterior probability. This posterior represents the model's calibrated confidence that a specific point pair is a true match. Now we need to combine these two posteriors. The authors assume conditional independence between the image and geometric evidence, given a true correspondence. Under this assumption, they derive a joint posterior using a Bayesian odds formulation. Mathematically, this means converting each posterior to log odds, multiplying the likelihood ratios from both modalities, and converting back to probability space. The result is a noisy and fusion rule, which heavily favors correspondences that are strongly supported by both modalities. They also implement a noisy OR variant, which acts more like a union operator and admits matches supported by either branch. Empirical ablation shows that noisy and consistently yields higher precision matches. In registration, precision matters more than recall because pose estimation relies on a small set of highly reliable correspondences to reject outliers during robust fitting. Because every component is frozen, this is a true zero-shot system. On indoor benchmarks like 3D Match and ScanNet, it matches or exceeds the performance of methods trained specifically on those splits. But the real breakthrough is on outdoor LiDAR data. C-GenReg is the first generative registration framework to successfully operate on real-world Waymo LiDAR scans. The adaptation here is clever. Since the WFM expects depth images, the pipeline projects the sparse, noisy LiDAR points onto a virtual f-theta camera. This wide-angle projection model handles the extreme field of view typical in autonomous driving, without introducing the nonlinear distortions that a standard pinhole model would create. The WFM then generates geometrically coherent RGB from this LiDAR-derived depth, providing the semantic and structural priors that pure 3D networks simply don't have. Runtime analysis shows that the WFM generation dominates the pipeline, taking roughly half a second per registration on modern hardware. This is expected when running a 7 billion parameter generative model, but the authors note that recent distillation techniques can reduce this latency by over 70 times, bringing inference down to roughly 7 seconds. The VFM and geometric branches each run in under a second, and the probabilistic fusion is computationally negligible. C-GenReg doesn't just push benchmarks, it shifts the paradigm. By treating registration as a modality transfer problem and fusing evidence probabilistically, it achieves robust generalization across sensors and environments without a single gradient update. As foundation models continue to scale, this approach proves that the future of 3D perception isn't about building larger networks from scratch, but about intelligently routing data through the right pretrained priors and combining them with mathematically sound fusion rules. The code and full technical details are linked in the description. I'd love to hear your thoughts on how probabilistic fusion might evolve in future 3D foundation models, and whether you see conditional independence assumptions holding up in more complex dynamic scenes. Thanks for watching.